So we have already done Narnia 4. So now we have to log into Narnia 5. And this is the password. Paste it and hit enter. Okay, we know where the data is. And if you type ls-l, and these are the two files that we need to worry about right now. So let's try to execute without any arguments Narnia 5, and it gives a segmentation fault. Okay, so let's try to run it with some argument. Okay, it now gives some data. Okay, change i's value from 1 to 500, and it also says no way, let me give you a hint. And then this is the buffer, and the buffer seems to be accepting this and storing it inside it, and this seems to be the size of this buffer, and there is a variable and looks like its value is 1. So let's change the payload and see what happens. Okay, so now we have changed the payload a little bit, and now the buffer has increased, and now its length is 8, and this doesn't change at all. Okay, so let's see what we have in the code. Okay, so let's see cat this, and this is the code. Okay, so we have some headers, that's fine, and this is the main function. This function accepts some argument, and I has been initialized to 1, and next we have a buffer variable which can accommodate 64 bytes of data. Okay, and then we have snprintf, and this snprintf has this buffer variable and the size of this buffer and also the value of argument that we are giving. Okay, so this argument has to store inside this buffer, and this line seems to be that the last character has to be 0, which means it can accommodate only 63 bytes of data. Okay, not 64. So printf, and this is what we have seen. Change the i's value from 1 to 500, and once the i's value is 500, then it just prints out good, and then it gives us the shell. Okay, and it also takes care of the user ID permissions and everything. If i's value is not 500, then we're going to get all these values here. Okay, and you also need to see this printf statement which says that I equals to %t, which means it is taking the value of I and printing it here. Okay, so initially the value of I is 1, and next thing it is printing inside the brackets, it's printing a pointer. And whose pointer is this? It's the pointer of I. Okay, so which means the value that we have got here is the memory location for the variable I. Okay, so we can use this to change the value of I. Okay, so once we have understood the code, let's see what snprintf can do. Okay, so if you Google for snprintf, it's going to give one of the links as this program is. So in this one, they have explained what snprintf can do. Okay, so this function writes string pointed to a format to buffer. So whatever is the format that we specify, that is going to be inside this buffer. Okay, and it also says that maximum number of characters that can be written is buff size minus 1. So we know the buff size, which is 64. 64 minus 1 is 63. So after the characters are written, a terminating null character is added at the end. If buff size is equals to 0, nothing is written, and buffer may be a null pointer. Okay, so they have mentioned this buff size is equals to 0, right? So this is where that statement is. Okay, cool. So this is the buffer, this is where this buffer is, and inside this code, this is that buffer. Okay, and the next thing is a buff size. So we have already seen that this is a buff size and the format that they have mentioned here. Okay, if you see this general statement, the third parameter has to be some format. Okay, so we can keep any kind of format right here. Okay, so this is where the vulnerability is. The vulnerability is in the format specifier. Okay, and this type of vulnerability is called format string vulnerability. So usually we specify a format by specifying this %sign and then some flags if necessary. If no sign is mentioned, then it just takes space. Let's say we keep something like % and then some character like, let's say X. Okay, so if we did not mention anything like plus or minus or something like that, so it's gonna simply take space as a character. Okay, so that's what this means. And then we have width, which is optional, and length, which is optional. We can specify the length. Let's say this space character, we can say that it has 20 bytes of spaces. Okay, that would be helpful. We have different types of specifiers, and if we say %, it means print, C for single character, S for string, I for integer, and then O for octal representation, X for hexadecimal representation. Okay, so when we give something like this, it is going to say that we are going to give hexadecimal representation of 20 spaces. Okay, so that would be helpful. We also need to have this n. Okay, so this n actually returns the number of characters written so far by this call to the function. So that's what this means. So this is the general format. So we'll use this to create a buffer overflow that would change the value of this I. Okay, let's see how we can do that. So let's keep some random hex value and see what happens. Okay, so we have already executed something like this, but this time, so let's keep a subshell, and inside this subshell, so let's create some hex characters. Okay, so this hex characters has to be pre-processed, right? So either you can use echo-e or you can use printf. Okay, so let's use echo-e. So let's give some hex characters, %hex41. We know that this is capital A, and then let's give 3 more of this. Okay, so let's see what happened. Okay, so there's a syntax error, which means, okay, so this has to be $, because this is a subshell, right? So we're creating a subshell over here. So let's see what happens. Okay, so we were able to successfully enter this into the buffer. So this will be pre-processed as A, and then it is stored inside this buffer. Okay, but nothing has changed with the value of I. Okay, what if we give the memory address instead of just random A's or something like that? Okay, so we know that the memory address of I is this one. Okay, so let's change this into the memory address of I. So we'll give it in little endian format. Okay, FFFF, and then D3, and then 70. Okay, so this is the little endian format of this memory. Okay, this will be pre-processed and this will be stored inside this buffer. We can see that this is stored inside this buffer. So we also know that if we mention the format specifier as %n, we can return the number of characters written so far by this call to the function. So let's see what happens if we do this %n at the end. So this is same and this one is same, but look at here, the value of I has changed, which means this %n has counted the number of characters, which means 4, and this number has to be stored inside this buffer, right? So what does this buffer contain? This buffer contains the memory address of I. So the value of I is changed right here. So far so good. So what if we give some spaces? So let's give some spaces, something like %20x. Okay, so if we did not give any plus or minus, this %20x will give 20 space characters. Okay, so we know that from here. Okay, since this one already has 4 characters and this one has 20 characters, this should return 24 characters, right? So this has to be changed to 24. So let's see what happens. So we got a segmentation fault. So why does this segmentation fault happens? Because it doesn't know where to store this number. Should it store in the first part of the argument or somewhere in the 20 spaces in the argument? Okay, so it doesn't know where to store this number. So we can specify that it has to store in the first part of the argument something like this. Okay, $1. So this $1 will tell the printf to use first argument in the list. This argument is the address of I. Let's see what happens. So nothing has changed here, but this has been changed. So why is that? Because this dollar is detected as a subshell. Okay, so we have to escape this dollar by using backslash, something like this. Okay, so now this thing will be detected as $1, which means first argument. Okay, and then the number will be stored inside this first argument, which will be the value of I. Okay, so let's see what happens. Now this value is same as previous, but this value has changed to 24. So what we want is not 24 but 500. Okay, so let's make it 500 by changing this value to 496. Okay, so 496 plus 4 characters here will give it 500. Okay, so let's see what happens. So as you can see, it detected that we got 500, so it said good, and it also gave us our shell. Okay, so let's say who am I, and we got Narnia 6. Okay, so let's print out the password, and we got our password. Okay, cool. So I hope you get it, and I'll see you guys in the next one.